So in this lecture, we will review the fundamental concepts and results in topological spaces. So the concept of topology generalizes our notion of open sets in the Euclidean space Rn. Okay. So consider a set X, a collection of subsets T. So in this case, we have a T, a subset of the power set of X, and recall that the power set of X is the collection of all subsets of X. So a collection of subsets T of X will be called a topology on X if we have the following three properties called T1, T2, and T3. So the first one is that the empty set and the whole set X must be in T. If you have two elements in T, the intersection must be also in T. And if you have an index collection or family of elements in T indexed by the set lambda, so this lambda can be finite, infinite, countable, or uncountable, then if you take the union must be in T. Okay. So if we have a topology T on X, then the pair XT will be called a topological space. Okay. And elements of a topology will be called open sets. So T1 would mean that the empty set and the set X are open. The collection of open sets must be closed under finite intersections. Okay. And a topology is closed under what we call arbitrary unions. So by induction, of course, you can extend a T2 for any finite number of open sets. Let's say if you have open sets U1 up to UN, then the intersection of these open sets must be also open. And these are, in fact, the properties of open sets in the Euclidean space Rn. Okay. Now, if the topology T is clear in the context, meaning if we know the topology on X, then instead of referring the pair XT as the topological space, we sometimes refer X as a topological space if there is no confusion. Okay, the complement of an open set is what we call a closed set. So here, tau C or T raised to C is the collection of all complements of open sets. Okay, so therefore, the complement of an open set is a closed set and vice versa. The complement of a closed set is an open set. Let us discuss simple examples. The first one is the trivial topology, and the second one is this discrete topology. So the trivial topology consists of only two sets, that is the empty set and the set X itself. Okay. You can clearly see that, of course, by definition, T1, that's the first axiom, is clearly satisfied. And if you take the union or the intersection, you either get the empty set or the set X. Okay, so indeed, this is the trivial topology, and it is the smallest topology on X. On the other hand, the largest topology is the discrete topology, which is the power set of X, meaning the set of all subsets of X. Of course, if you take the intersection two subsets of X is still a subset of X, and if you take an arbitrary union of subsets of X, then obviously it is also a subset of X. Okay. So these are the trivial examples. The smallest topology is the trivial topology on X, and then the largest topology would be the discrete topology. So for the trivial topology, the only open sets are the empty set and the set X, nothing more. And on the other hand, for the discrete topology, all subsets of X are open. Another example which we use typically in analysis or undergraduate analysis is the so-called usual topology on R. Okay. This means that set U of real numbers will be open if, let's say, you pick any point in X, then you can find an interval containing X and lies entirely in U. And one can show that this is indeed a topology on R, and we will call this the usual topology on the set of real numbers. So you can pause this video and verify this example. So next, with regard to comparison of topologies, suppose I have two topologies, T1 and T2, on a set X, and T1 is smaller than T2, meaning T1 is a subset of T2. Then we will say that the smaller topology weaker or coarser than the larger topology. And on the other way around, T sub 2 will be called stronger or finer than T sub 1. The term coarser and finer comes from the analogy that you can, if you think of topology as a collection of sand, then the coarser topology, meaning it is a collection of gravels which are coarser or larger. And in the case of finer, your stones or your gravels are smaller. The next discussion would deal on construction of topologies from older ones. Okay. So the first one is what we call the subspace topology. So suppose I have a topology on a set X, and I take a subset A on X of X. Now, we want to put a topology on this subset A. What we could do is we take the collection of all intersections of open sets in X with A. And one can show that by simply applying the properties of in set theory. One can show that this indeed a topology on A and will be denoted by T sub A. So in this case, so I have a topology on X, I have a subset A, then a subset of A would be open if I can write this as the intersection of A and an open set U in X. So this is the construction of open sets on a subset with respect to a given topology on the larger set X. Okay. Next, we have the so-called topological basis or a topological base. not to be confused with the concept of basis in linear algebra. So let us look at the definition. A collection B of subsets of X is called a basis or a base if, okay, you take any X, small x in the set, you should find a B in the collection script B that contains X. The second condition is that if you have B1 and B2 in the collection, and if you have a point in the intersection, then one can find a B3, a third set in the collection script B, okay, such that X is contained in B3, and this B3 is contained in the intersection. Okay. Well, this basis generalizes, let's say, the properties of open balls in, let's say, in the Euclidean space, because any point is contained in an open ball. So you could just choose any positive distance r. Now, if you have two open balls and they have a common point, then you could find an open ball containing that point, and it is contained in the intersection. So this topological basis generalizes those properties of open balls in the Euclidean space. Okay. So what is the significance of a basis? A basis, or a topological basis to be precise, generates a topology. So suppose I have a basis P, and I collect the set of all subsets of X in such a way that, okay, you pick a point and this X here, you can find an element B of the basis, also called basis element, in such a way that X is contained in B, and this B lies entirely in the set U. So a different X would mean a different B in general. Okay, so your basis element B depends in general with the point X that you take in the set U. And one can show that this is indeed a topology on X, and this will be denoted by T sub B. An alternative characterization of this topology is the following. This topology is also the collection of all unions of subcollections of B. And this justifies the term basis. In other words, open sets with respect to this topology are nothing but unions of elements of the basis. So, as I said, the basis elements in this case form the building blocks with respect to this topology T sub B. Well, there's a smaller. One can go to the concept of the so-called topological sub-base. So what is a topological sub-base? So given a collection S of subsets of X, we will call this a sub-base if you take the union of all elements of the collection, you get the entire set X. So that's a simple uh, condition. So if you take all the unions, if you take the union of all elements and it is the same as the set X, then we call this a subbase in X. Well, with respect to this subbase, okay, we can form I of S. And by definition, this is the intersection of all finite subsets of S. So you take a finite subcollection of S, say F, okay, then you take the intersection of those sets, then you have this collection I of S. And one can show that this is indeed a basis, and we know that if I have a basis, I can generate a topology. And this topology will be denoted by T of S, and using the alternative characterization, it is the union of elements in a finite, in a subcollection of I of S. So a typical element would be the following. So you would take the union of all U, but an element U would be of the form, which is the intersection of some finite subcollection F of S. So the topology generated by a subset is the union of intersections of elements of the subbase. Again, you can pause this video and verify these claims. Now that you have verified that a subbase generates a topology in this manner, we could give a topology on the product of two sets. Okay, so suppose I have a set X having a topology T sub X and a set Y having a topology Ty. So the task here is that we would like to generate a topology on the Cartesian product X cross Y, which is by definition the set of all ordered pairs, say XY, where the first component X is in capital X and the second component Y is in capital Y. Well, what we do is that we construct the Cartesian product of the two topologies, which is by definition is the collection of Cartesian products of the respective elements of the two topologies, the one in X and the one in Y. You could see immediately that this is indeed a subbase because, as we know, X is open in X with respect to the topology Tx, and Y is open with respect to the topology Ty. Therefore, this is an element of this Cartesian product of topologies. So therefore, the whole set belongs to this Cartesian product, and automatically the union would be X cross Y. Thus, as we have said, this is indeed a subbase, and if you have a subbase, you can generate a topology of this subbase based on the previous discussion. So how would we construct again the open sets for the topology generated by a subbase? As we said a while ago, you take the arbitrary unions of finite intersections of elements of the subbase. And in this way, this Tx cross Y will be called the product topology induced by the topologies Tx on X and Ty and Y. And of course, you can, by induction, extend this to a finite number of topological spaces. Okay. So given a topological space X and a subset A of Y, so A here is an arbitrary subset. It is neither open nor closed. We can talk about the interior of a set. So the interior of A, denoted by A circle, is the union of open sets that is inside A, So you can obtain the interior by taking or combining all open sets that are contained in A. And one can show that the interior is in fact the largest open set that is contained inside A. Well, if you can think of it, this is basically, or it can be proved easily from the definition because you are combining all open sets inside A. There's also what we call the closure of a set. So the closure of a set will be denoted by A bar. And this A bar is what? It is the intersection, okay, of closed sets that contain A. So recall that TC here is the complement of open sets, therefore they are the closed sets. Okay, one could show that simply by using De Morgan's law that the arbitrary intersection of closed sets is again closed. Therefore, the closure is a closed set, and by definition, it is the largest closed set that contains A. So again, the interior of a set is the largest open set that is contained in the set, while the closure is the largest closed set containing the given set. And then subtracting the interior from the closure, we get the so-called boundary. And it will be denoted by partial A. Okay, this notation can be, let's say, roughly explained in the Euclidean space, let's say two-dimensional Euclidean space. So if I have, let's say, a set A, okay, a point is on the boundary if there's a region that is inside A and that is also outside A. So you can think of it is part inside A, but part outside A. And this boundary is closed because you can write, of course, the set difference as the intersection, in this case, of the closure and the interior. Okay, and we know that A bar is closed. The interior of A is open, therefore the complement is closed. So the intersection of two closed sets is also closed. There is also the notion of compact sets, which play an important role, for instance, in the field of optimization. So suppose I have a topological space X and a subset K. Then we say that this set is compact, or more, in some cases, they call this covering compact. If I have, or for all collection of open sets whose union contains K, and this way we say that it is a covering. Okay. So if I have an open covering of K, I can find a finite subset or a finite subcollection that will still cover the set K. So put in another way, a subset of a topological space is compact, or if you want to be precise, covering compact, if every open cover has a finite subcover. So in this picture here, let's say this is our compact set K. Okay. Then probably you can cover this by, so if you have a covering, you can reduce this covering into a finite subcover. In other words, it is possible to choose a finite number of open sets, and with those finite number of open sets, you can still cover the set K. So in order for K to be compact, all open coverings should be or can be reduced to a finite subcover. And I would like to mention here that, for instance, in the case of the Euclidean space Rn, the compact sets are precisely the sets that are bounded and closed. And this is called the Heine-Borel theorem. Okay. Well, this is a typical feature of finite dimensional spaces, but we will see in future lectures that this is not the case of infinite dimensional vector spaces. The next definition would be on separability. So given a topological space X, a subset D will be called a dense if the closure is the whole topological space. So for example, in the case of R, the set of rational numbers is dense in R. Of course, R having the usual topology that we have defined a while ago. Now, if your topological space has a dense subset and this dense subset is countable, then we call the topological space a separable space. Based on our example, R under the usual topology is separable, because a dense subset would be the set of rational numbers. And as we know, the rational numbers is countable. Of course, in general, you could also deal with the Euclidean space Rn, and a dense subspace would be Q sub n. In other words, this is the Cartesian product of Q n times. So you have tuples, n tuples of rational numbers. And one can show that this is also dense in Rn. Okay. Rn here is our usual topology. And in this case, Rn would be separable. Additional examples will be given in future lectures when we discuss function spaces. Okay, the next would be what we call a Hausdorff space. So a topological space X will be Hausdorff if for every distinct points in the space, I can find two open sets U and V, where U contains X, Y contains V, and they have no common element. So we have this figure here. So you take any two distinct points, say X and Y in the space. One should be able to find two open sets that would contain these two distinct elements and that they are disjoint. So this is some sort of a separation action. And its significance later will be emphasized in the case of convergence. Classical example, of course, the Euclidean spaces are Hausdorff spaces. Because you can choose these open sets to be open balls. Recall that in our introduction, we have this motivation or the goal wherein we want to define notion of convergence. Okay. And as we have said, the notion of convergence, for the notion of convergence, it is enough to have the concept of open sets. So how do we define convergence with respect to a topological space? So let's look at the definition. A sequence, say x sub n from 1 to infinity, and in future discussions, we shall simply denote this by x sub n. Okay. So a sequence x sub n in a topological space X is said to be convergent if there exists an X in the space for which, if I choose any open set U, this shaded region here, I can find an index n. Well, this n might depend, in general, depends on the open set U that you take, such that, okay, the terms of the sequence having indices that are greater than or equal to this number capital N should be inside U. Meaning, all except for the first n minus 1, possibly the first n minus 1 terms of the sequence beyond index n, or possibly n, all of the terms will lie in the open set U. Okay. As I said, this n here can depend in U. Because let's say I have a smaller open set. So if I have this open set here, call it again U for simplicity, then you need a larger index in order to satisfy this criterion. And if this is the case, we will denote X by this notation or xn converges or approaches to x as n goes to infinity. If the index set, in this case, the natural set of natural numbers is clear, then we sometimes remove this portion here. So we are borrowing the notation in calculus. Okay. Well, convergence of sequences in general topological spaces can be weird. For instance, in the case of the discrete topology, that is the power set of x. Okay. A sequence is convergent if and only if it is eventually constant. In other words, it must be of the form x of 1, x of 2, x of 3, and then after some, let's say, x of capital N, all of these terms are equal. So that is what we mean by a sequence that is eventually constant. After some finite number of terms, the terms will be the same. So in this case, the convergence of a sequence is very limited because in this topology, the discrete topology on X, we have all subsets to be open, which means that we have more open sets. And in that case, we need to verify this condition for all subsets. So with respect to the discrete topology, convergence is very limited because you have more open sets. On the other hand, with respect to the trivial topology, in fact, all sequence would be convergent. And it will converge to any element of X. That is because you only need, for instance, if I have a sequence, this will converge to any X because the only open set that would contain that point would be X. And in fact, the open set X contains any element. Therefore, any element would be a limit. So that is also not interesting. So in trivial topologies, any sequence would be convergent and any element of the space would be a limit. This comes from the fact that the only open sets are the empty set and the set X. So there's only few. In fact, only two. Okay. Well, to guarantee that we have a unique limit, then one could impose the condition that the space must be Hausdorff. Okay. Well, to see that, for instance, if you have, let's say, a limit x and a limit y of your sequence, then if x is the limit, this will contain all except for a finite number of elements of the sequence. Okay. So in other words, outside this open set of the limit would be only a countable number of elements or a finite number of elements of the sequence. And if you have a point y, disjoint or distinct from x, you can find a neighborhood of y, this case denoted by v, that is disjoint from u. So therefore, this y will only contain a finite number of elements of the sequence. And by definition, that would not be a limit of the sequence. Because in order for a point to be a limit, you pick any open set containing that point. It should contain all terms of the sequence except for a finite number. So to guarantee uniqueness of limits, one could impose the condition that the topological space must be Hausdorff. So next, we will discuss continuity of mappings from one topological space into another. So suppose I have two topological space, X and Y. Okay. And here we have this figure. So the domain would be a topological space X. The codomain or the target space would be another topological space Y. And I have a map or a function from X to Y. This function will be continuous if you take any open set V in the target space, the inverse image of this open set, F inverse V, must be also open in X, meaning it is an element of the topology T sub X for all V in T sub Y. Okay, take note that F might not be invertible. So the inverse image is defined in this way. So recall that the inverse image of V, let's say V, a subset of Y, is the set of all points in the domain X, wherein the image under the function F is an element of V. So if you take X, it will be mapped to F of X, and this F of X must be in V. That is the definition of the inverse image. It has nothing to do with the inverse of a function in general. Okay. So to verify continuity in general topological spaces, this can be done. The inverse images of all open sets in the target space Y must be open with respect to the topological space X, which is the domain of the function. Okay, so that's it for topological spaces. And it is a fast review. If you are interested, you could look for standard text in topology. And for the proofs, you could verify or read them in your free time. So in the next lecture, we'll be considering metric spaces. So see you then.